presentation today will be on anti-money laundering alert enhancements. So taking a look here at transactions that occur at banks. They currently use what's called rule-based AML alert systems to flag and adjudicate suspicious transactions, right? As we've discussed in class, rule-based logic scales poorly, it's difficult to maintain, and creates challenges for exception handling. And this is especially an issue when criminal transaction patterns are constantly changing to adapt to the rules that are set in place, trying to catch them, of course. So it's a game of cat and mouse. And naturally, this will create a very high false positive rate from these rule-based systems, which has both a negative impact on internal processes, but it also has an impact on customer relations. Since manual labor doesn't scale very well in terms of cost, and current transaction volumes are expected to double by 2030, high false positive rates in manual processes during these flows lead to a very high labor cost and forecasted labor cost, which can create limited resourcing used to combat AML. And you can see that in the success rate of a lot of the expected laundering in the world today. Is over $1.5 trillion per year laundered, and less than 1% of that is actually confiscated. So focusing on these challenges today, we wanted to explore if machine learning could help. So our project, we aim to develop a machine learning model that can improve scalability versus rule-based logic, minimize false positive rates, and increase productivity of labor, or reduce manual labor, making sure that we respect individual contributors, not to replace everybody, but to augment and speed up the experience as transaction volumes are expected to increase. Right? And so the method that we'll be exploring today is, of course, binary classification, and that's looking at flagging transactions for suspicious activity or not, right? As far as the data that we worked with goes, the data set we chose to use actually builds on real data from a Danish bank and contains 20,000 AML alerts and over 16 million transactions associated with those alerts. They're broken up into two tables, alerts and transactions. Alerts were sampled from a subset of the rules and models used by the bank to currently detect fraudulent activity. And for every alert, the dataset pulled the last 365 days of transactions and stored them in the transactions table. For this synthetic data set, bootstrapping was also used, which is random sampling with replacement, to ensure that the stratified data contains a 50-50 split between male and female clients and a 10-90 split of high-risk versus non-high-risk clients from an AML perspective to try to generalize. It should be noted, too, that noise was added to the transaction sizes and timestamps to protect client confidentiality. We'll get more into this later, but that type of policy and concept within the financial world is a big challenge in terms of communication, but also for a lot of these models, which is why this synthetic data set was created, in order to see if it could be used as a way to train potential models like ours in order to detect fraudulent transactions. So we started to explore the data. It was fairly straightforward. First, we just made sure that there was no missing data. Next, we discovered that the data set was unbalanced, and therefore we needed to do stratified sampling and look at precision recall, F1, ROC-OC as our performance indicators. It's to be expected, right? Of the trillions of transactions that occur every day, we of course are only going to have a subset of those be fraudulent, so it's no surprise that the amount of flagged transactions are significantly lower than dismissed, right? We can also see here just some interesting trends, how the transactions were split between credit and debit transactions, along with the type, so wire, card, international, and cash, different ways that money can move around the system. And of course, the associated sizes of these transactions can vary from method to method, with international, of course, being the largest. But what's not shown here is very low sampling within our data. And you can see that the scale or the measurement of the size has already been transformed using log DKK, which helped pre-processing and primarily served as a way to protect confidentiality as well. From this, we wanted to see if any useful features could be engineered, in which, as I mentioned, because the authors have already standardized all transaction sizes, some amount of data snooping is inevitable. We ended up calculating summary stats, so max, min, mean, standard deviation for transaction sizes, and then we repeated that for data by entry and type, right? And then for each combination of entry and type, we created 365 associated columns to coincide with the transactions to see if we could get any kind of temporal data as features, and to see the occurrence of different transactions throughout those days. So for some entries that were unavailable, as I mentioned earlier, that international had a very low count overall, when we're splitting, for example, by 365 days, of course, we're going to get a lot of zeros. So what was interesting with our project is for missing values, we imputed values of -3, as suggested by the authors of the data set, as -2.9 was the lowest observed because this had already been scaled, right? So some values are lower than 0. Once we created a bunch of features, we then wanted to see which ones were useful. So we did a quick feature importance exercise, and we ran a few models across the 2658 features. We trained stochastic gradient descent, random forest, gradient boosting, XGBoost, and logistic regression. And from there, we calculated the average feature importance and took the top 50 features to see the impact on training time. So we went from, almost 3,000 features down to 50. And before we get to our changes there, a quick snapshot on how model performance was at baseline. So this was with, just running default settings for the different methods. We can see that, precision and recall for the test set, these are the positive classifications, so the ones, is quite low, and the area under the curve is quite low as well. Basically signaling that it's likely up to random chance that we see any kind of relational ability to flag transactions from our data, but we wanted to see if we could improve this. And what we did there was we retrained random forest, gradient boosting, and logistic regression with the top 50 features, and measured the effects on that. We then also took a look at hyperparameter tuning to see how that would impact our metrics as well. So this comparison here is just showing where we went from our baseline with 2,600 features to the 50 features that we ended up with, and you can see the massive impact on training time, especially with gradient boosting as a classifier. Significantly impacted well. A lot of the core stats were maintained, and some even got worse, like the gradient boosting there. And so once we did some hyperparameter tuning, we reached the threshold of our ability to impact and reduce overfitting within the model here. And the hyperparameter tuning had minimal impact. So what we drew from this, we took a look at the performance of the authors success on the synthetic data, and it actually coincided quite well with our own performance. You can see their results on the left. And what was interesting was they had access to the actual real transaction data. And it's not shown in this chart. But when they ran it against the real transactions, the ROCAC score went from about, the 62, 63 there for random forest, for example, up to 75%. So what that signals to us is, we are limited in our ability with the synthetic training set, but we may be able to get some more success if we were able to scale this and expand the data set, and of course use real transaction data, especially with more fidelity and more features, to see if we can signal for fraudulent transactions more effectively, right? And we were happy with our ability to perform, comparatively to the original authors. But again, this is kind of a play set, if you will, and we weren't expecting any significant outcomes from this, rather as a good exercise to go through the motions and explore the processes of putting together some of these models. And given that we were close to the original author's performance, we were satisfied to validate that, there is plausibility in being able to predict and use models within financial institutions. Many have already adapted models, much more powerful than this, of course. But I think it is important for everyone to get on board and encourage this type of thinking within the industry. I think the other big thing to mention here is the difference between false positive rates and false negative rates, right? Within this space, the false positive rate is already astronomically high, so it is safe to be able to play with the threshold there for some of these models to allow for some more false positives in order to capture more of the true positives by playing with that threshold value there. And you can see the trade-off curve on the right, where if you compare some of the manual processes that have 90 to 95% false positive rates, if we were to increase our range and score our flags based on probability, that could still improve processes. So manual operators, at least have a prioritized or stack ranked list of alerts to process through, while still being better than some of these rule-based systems that are in place today. The other caveat here too is, because transactions change all the time, and especially with money laundering application, the ways people can launder money change over time. We need to make sure that if we were to scale this project, we would be looking at building real-time machine learning models in order to consider this landscape, right? Because we want to keep up to date with what the current strategies are for evading the system, and our model needs to be able to quickly adapt to that and scale. And what's nice about some of these real-time models is you don't need some operator to figure out the pattern, manually implement that rule, then roll it out in order to catch some of these transactions. There's a lot of opportunity here to scale them in industry. So in summary, some of the lessons we learned was, the alerts were used to simulate synthetic data. So the entire data set already came from alerts. So strictly speaking, that kind of introduces a form of target leakage. We were aware of that. We're not trying to actually implement this into production today. Our priority, of course, was demonstrating that end-to-end workflows I mentioned and exploring how machine learning can enhance these workflows. We'd also want to build the model based on, real transactional data, not just data associated with an alert, because of those biases. So we'd love to take a next step like that. We also understand that our data quality wasn't best, and due to some of the confidentiality challenges, it'd be hard to get a comprehensive transactional or account information in our hands. But in practice, of course, we'd want to take a look at some more features like IP address or geography, country, KYC status, and more about account balances and details to see if that could lead to any meaningful signal. Some of the technical items that we learned here I have up on the screen. the first one, it's being crucial to have informative data and engineering features that can distinguish the two target classes. Given the basic nature of the data set we worked with, we'd love to see something that could be a little bit more descriptive in order to have better signal at differentiating those classes. That showed a much greater performance compared to random chance. We also saw a lot of more conservatism in random forest, which of course was more positive prediction, and it's a little bit more explainable. So that's one area I didn't really cover yet in the presentation, explainability. Some of the models that we use, especially when we are flagging fraudulent transactions, and there are legal implications of that, being able to explain how that transaction was flagged to build a legal case is very important. So that should be another consideration when putting this into production as well. We found that the gradient boosting tend to overfit, so fine-tuning those parameters could help regularize it. We saw that there was the biggest change in gradient boosting once we did hyperparameter tuning. And then, of course, that drastic reduction in training time, pretty obvious through dimensionality reduction. So long as we're preserving the signal, great way to make things more efficient, especially if we are working with real-time systems. And the biggest takeaway from this is you can only do so much with the data you have. So being able to get access to more data in order to build a more comprehensive model, really important. But this is one of the big challenges in the space, in the industry in general, is just that lack of data availability. And projects like these, like ours, and even the project to put together a synthetic data set is really important, so that multiple banks can work together and build some of these systems out and bring up the laggards, so that they are handling best practices when it comes to money laundering. Because data is very sensitive and not likely to be shared, it is very hard to get these performant models outside of the black boxes that may exist at the big five banks, for example. They're going to have their own systems, but some of the smaller banks may not have the means or the capabilities of building their own in-house extensive systems. So would love to see more work in this space, and it was a very interesting project to take on and learn a little bit about. Thank you.